So now we have looked at sequential consistency as one memory model, but when I asked the trick questions, I said we can't define what what these executions will result in because we haven't defined what the memory model is. So you have probably already figured out that there are many more memory models than just sequential consistency. The memory model which is maybe closest semantically to sequential consistency is a memory model called total stored order, which was introduced by Pradeep Sindhu, or TSO for short. I try to make a picture of what a total store ordering model is. So it's a model where you have all the threads once more executing as fast as they can, but whenever they would like to perform a store operation, they can buffer that for a little while, but before that store operation makes it out to the shared memory, it has to be selected by this big switch here. So the implementation looks like, of total store looks like, we perform a single store operation from a single one of these threads at a time. So that's why the name is total store order. There is a global order between all the stores that's been performed by this software in the world, and nobody should be able to write a piece of software that detects any other kind of order than the global order. This means that programmer's intuition is almost maintained, because this is often what we have in mind, this kind of, there is a global order between the stores. Load is a different business. The loads are not ordered in this global order. Each of these threads can perform a load that can potentially bypass its own stores, and it can make one load at a time to the shared memory. Still, programmer's intuition is almost maintained. But once more, it does leave a little performance on the table. It performs much better than sequential consistency, but there could still be some room for improvement. Before we look at even weaker memory models, let's understand the properties of the total stored order system. So this is an example how you can implement the total stored order system. So from the cache lecture, you may remember that we often have something called a store buffer in CPU implementations, and that is simply a placeholder where you can put the stores. You can let them age for a little bit there until you have the time to perform the stores to the shared memory. Meanwhile, you can let the loads bypass. And why is that important? Well, because loads return some value that you need for so you don't have to store the pipeline. So loads are actually more important to be performed than stores. So this is a huge performance boost to introduce this store buffer. However, in order to not confuse the programmer too much, when you have this kind of store buffer, you have to make a comparison, as you may remember, between all the entries in the store buffer, the new values on their way out to update the shared memory, such that if one of the loads is to a value that you have promised to make an update to, stored here in the store buffer, then the new value should be returned for that load. So we have comparators sitting here, comparing each load, the address of each load, with the address of the stores that are on the way to the shared memory. So this is one possible implementation. The network here could potentially be a sequentially consistent network, or a highly ordered network where the loads of stores are ordered. That's maybe a little overly restrictive because once more, we have only defined the order between all the stores. At this point, when they reach this point in time, the order between the stores should be put in a global order. Okay, so now we know that we have some total store order system. We know that all the stores are globally ordered. Then we can ask, and we can look at our favorite example again, and we can ask ourselves, in this system, total store order, which is slightly weaker than sequentially consistent, what value do you get printed? Well, since this store here, store of A, happened before the store to the flag, then that is the global order that has to be observed by everybody else. So the order here, because that order is going to be maintained in that queue, and that order has to be preserved by the memory system. So since we see that flag changed value here, that means we also have to have seen that A changed value. That's thanks to the global order of stores. So correct answer here is once more 1. What about this example, the partial correctness example? So once more, here's the value change order and the program order is defined in this simple example. Given total store order, what value will get printed? So once more, there is a global order between stores, which means that if this node in the middle has observed that A has changed value, and that observation they did right there, after which it performs a store operation. That means this store operation must be ordered after the observation of the store operation to A. So now it's been determined the global store order between A and B is that A happened before B. That means that since we can observe that B happened with the while statement here, it means that A must also happen. So X will get the value 1. This is slightly weaker than sequential consistency, but we didn't need the ordering of loads versus stores. We can just look at the value of stores to make this partial correctness work. Finally, what about Decker's algorithm? So given total store order, is it possible that both threads win? Another way to phrase that question is, does the right of A equals 1, does it become globally visible? Is it put in the global order before the thread is able to perform this load operation? So unfortunately, the answer to that question is yes. It is possible that both threads win if you execute this piece of code under total store order, and that was not what Decker had in mind. So that means that this piece of code is broken. Can you fix that? Is it so that you can never write Decker's algorithm under total store order? It's easily fixable. What you will have to do as a programmer is to detect the situations when you need an order which the memory system cannot give you. In this example, it's the order between performing a store operation and the loads following it. There is a very simple intuition why you can't rely on this ordering, and that's the fact that this store can be put in the store buffer, while this load can bypass that store. So this store still sits in the store buffer, and it's not going to get globally ordered until it gets out of that store buffer. The way to fix it as a programmer would be to put in a memory barrier. And the memory barrier says, hold your horses, Mr. Hardware Implementer. Right here, I tell you that you cannot go on and perform the next load operation until you can guarantee for me that all the previous stores have been performed. How can I, as a hardware implementer, guarantee that? Well, all I have to guarantee, looking at the previous design here with the store buffer, is that whenever the programmer puts in this memory barrier instruction, I have to make sure that the store buffer is drained, so that all the stores in that buffer have been globally performed, have been put in global order. And only after that am I allowed to go on with the execution. So with a little help from the programmer, inserting memory barriers in the right place, and once more, total store order, you have to insert a barrier where you want you want loads following a store to actually be placed in the global memory order in exactly that order, load after the store. There are lots of even weaker memory models. So there is something called weak consistency or release consistency, or weak memory models and release memory models. They were proposed by Michel Dubois and Kourosh Karakolou, respectively. And here, in a simplified picture here, what's going on is, we don't guarantee anything. You, as a programmer, have to really be on your toes, and you have to help us. You have to tell us all the time that you care about where you want things to be ordered. That means that if you as a programmer don't do anything specific, that means that none of these cases, flag synchronization, caution correctness, or Decker's algorithm will work. So the global order is only established when you explicitly insert some memory barriers. And in the case of release consistency, Kurush-Karakulo also said that, talked about the semantics that you have when you acquire and release lock. So that we will discuss this in a little while, the implementation of critical regions, but that all you have to remember here is that release consistency is sort of related to that as well. But in some sense, you will still have, as a programmer, have to insert memory barriers all over the place. This is good for performance because this puts very little constraint on me as a hardware person to how I implement the system. It's a coherent system, but I don't have to establish some kind of global order between the transactions. It's fine if I only establish coherence for each of the pieces of data or each of the cache lines stored in this memory, but not between the changes that happens to many different cache lines at almost the same time. So better performance, but also very interesting bugs, because it's tricky to understand where you need to insert these memory barriers. For example, in the case of the flag synchronization, you have to insert a memory barrier after you change the value of A and you change the value of flag to establish order between this store and that store. Here, you have to insert a memory barrier to guarantee that there is a global order between this load and this load over here, load to load order. Okay. Decker, you have to make the same changes as for TSO. So you have to insert the memory barrier between the load and store on both the left and the right side. In caution correctness, also need memory barriers inserted every time you would like to establish an order. So it's tricky. It's tricky, but there is good performance. And some people really would like to expose this kind of ordering to the programmer anyhow. And this is which memory model is better? Well, that's a highly religious question. It's like asking which programming language is best. So people tend to walk around with lots of different opinions about this. Let's look at yet another programming model. This is the last one we're going to look at, and it's something called processor consistency, which was defined by Jim Goodman, the first person with the Snoopy protocol. And processor consistency, or PC for short, is like a special case of total store order. It says that all the stores that are performed from a specific process, so we're just looking at all the stores that's done by one of these threads, all those stores appear in exactly that order all over the system. Okay? So flag synchronization works because flag is written, both flag and A is written by the same processor. Caution correctness, it's actually not clear if caution correctness works because Jim Goodman, he forgot to cover that case. Other people that has referred to his work say that he probably just forgot to define it. But if you hear somebody talking about processor consistency and you would like to establish the fact that caution correctness is implemented, you really have to specify that because you cannot assume that from just the process consistency. So maybe caution correctness works if it's program consistency with caution correctness, then the caution test, the second example, really works. Decker's algorithm will not work, so this is similar to, this is a weaker model than total store order, so that really wouldn't work either. So I hope I gave you an impression of what memory models are, why they are important. However, the purpose of this lecture was not to really define down to the smallest detail exactly what all the semantics and all the corner cases are in memory models. There is a very good paper which is in the papers directory of this course, written by Sarita Adve and exactly the release consistency guy, Kurush Garakudo. It's a bit hard to read, but it's a fairly complete paper, I feel. Um, um, Before you start to program a system, especially if that system is a based on PowerPC, you have to sit down and try to figure out what's going on. And unfortunately, I met people working on PowerPC that claim that nobody understands really what the memory model of PowerPC, the high performance PowerPC really is. But read the manual and try to figure out what's going on. I can warn you, it's going to be a little troublesome. And things that you may want to think about is given this stuff about memory ordering and how important that is it okay for a compiler? You know, compilers often reorders instructions and optimize. What kind of reorderings can a compiler do? Can a compiler ever move a load and a store past each other? It's not really clear. It depends on the memory model. And also, what does the volatile declaration in C mean? So volatile declaration actually implies two things. One is what volatile says, this is a scary variable, take special care of it. But what that implies is a volatile declared variable in C can never be assigned to a register because it's a volatile, it's a global variable. And if you put the variable into register, then you take it out of the coherent world, you take it out of the global world, nobody can see value changes to it, and the thread performs to that variable, and it cannot see any value changes performed by anybody else. So that's scary. But what also volatile means is that there are restrictions on what kind of optimizations compilers can do, how they can move those instructions around. So this is something that you will experience during the next lab, how important volatile declaration really is in a shared memory program. So finally, x86. So x86, as you know, has been around for many, many years, and its memory model was very ill-defined until a couple of years ago, when people started to use it more and more in multi-cores and in servers, and they felt that they had to sit down and rethink what the memory model of the IA64 really was, the 64-bit instruction set. And they came up with a statement saying that it's it's processor consistent with partial correctness for non-atomic memory operations. So processor consistency with partial correctness, okay. And it's total store order for atomic memory operations. We haven't defined what atomic memory operations are yet, but this is the definition that they came up with, and it's overly complicated to understand what's going on. Academia took a look at this, and many papers have been written from academia where they claim that what the really true memory model of x86 IA64 is total store order. So, I put a link to the input manual as well down here, section 8.2. They do discuss this. And just for laughs, if any of you are interested in how complicated this could be, there is a clip on YouTube, and that clip shows a presentation by the Intel people at Google. So Google have big seminar series where they invite smart people to talk about interesting things, and the memory model of x86, for apparent reason, is very important to Google. In Google, so for example, that Kurush Garakudo, he works at Google. Many people who have been active in memory models do work at Google. So these people from Intel came and they wanted to finally explain what was going on. And as you can see at that video, there is a huge confusion about what memory models are. It's not even these people who are active building the chips and defining the memory models, and probably the most advanced users you can think about clearly can wrap their head around this. So your take-home messages, memory models, they are important. They can be tricky, and you really have to understand the memory model of the system you're programming. If you start to do lots of hanky-panky code, if you stay in OpenMP or some library way of creating parallel execution, you may get away with just understanding what the memory model